Our next example here, I left something out. We have the integral from, we have negative infinity for the lower limit, 0 for the upper limit, and we have the integrand is x squared times e raised to the 2x cubed dx. Now I want to make a little side note here off to the edge here. Just for our infinity arithmetic's purpose, negative infinity raised to the third power, remember what that means in a very plebeian way. We can write that infinity times infinity times infinity is infinity in our infinity arithmetic, and negative times negative times negative is still negative. And so negative infinity to the third power, we will interpret that to be negative infinity, and then we're off to the races. So when I say that, because that's going to arise in this computation, I want it to just sort of be hanging there for us to be able to use here. So what do we have here? This is the lower limit of integration is infinity. And so we're going to write this as a limit statement. I'm going to use A. I will typically use A for the lower limit of integration, B for the upper limit of integration. And now this is from A to 0, x to the second, e raised to whatever we have here, 2x to the third. All right. So the integrand stays the same, the differential stays the same. All we've done is we've changed integral sign negative infinity to 0 into integral sign a to 0, and then the limit as a goes to negative infinity. Our process is evaluate this definite integral, evaluate at the top minus evaluate at the bottom, simplify that, and then evaluate this limit. Now, in order to evaluate this limit, this is a u substitution. So let u equal, this is a function being raised to the power of another function. And so this is, let u equal 2 times x to the third. The differential is 6x to the second dx. I don't want 6x to the second, I just want x to the second. So we can get rid of this 1/6 du. And so the substitution is now exact. We have e raised to the u, all of this leftover bit, I'm sorry, this is 6x to the second. And so all this leftover bit is exactly what we want it to be. The substitution is exact. And so now we can write this as, it's going to be the limit as a goes to negative infinity. Now, what I'm going to do is this. The limit ultimately is in terms of the variable a, but we've done a substitution, which means these limits are no longer accurate. If I write, this is e to the u, du, and I need my 1/6 here. Now, let's worry about the 1/6. The 1/6 could be in here, the 1/6 could be in here, the 1/6 could be in here, and the 1/6 could be out in front of the entire limit. So I'm going to take my 1/6, if you don't mind. Constant multipliers multiply along with both integrals and limits. So I'm going to take this constant multiplier and throw it clear out in front of the entire expression. And I need to know that when I get my final result from all this mess, multiplied by 1/6. So that's taken care of. But the another important piece is this. If I write a to 0, that is wrong because these limits go with the x variable. This integral is a u variable. This is wrong of wrong, wrong. This does not equal that. This is wrong. So what I'm going to do is, one option is you could translate the limits. That becomes kind of persnickety here with this expression here. You could translate the limits of integration, but a better version is this. Put in dummy limits of integration. Just put in dummy limits of integration. And then when we go back to the original variable x, we will go back to the original limits of integration, a and 0, and then we'll be off to the races. Dummy limits of integration. The devil is in the details, and this is loaded with them. So what do we have? 1/6, limit. A is going to negative infinity. Okay, the antiderivative is e to the u. This is evaluated from c to d, which values I don't know yet. But now we go back to the original variable, which means we go back to the original limits of integration. The original variable, u, was equal to 2x to the third. And now this is evaluated from a to 0. And so what's our rule? Evaluate at the top minus evaluate at the bottom. So we have 1/6, still have limit. A is still going to negative infinity. But now evaluate at the top minus evaluate at the bottom. That's why I like to take this constant multiplier out front, so we're not fiddling around with it over here. So e raised to the, when you substitute 0, this becomes e to the 0, right? Substitute 0 in for x. So this is e to the 0 power, but then this is e raised to the 2a cubed. Substitute a in for x, 2a cubed. E raised to the 2a cubed power. And now, when we do the actual limit, so we've evaluated the limit, we've substituted the upper limit of integration, the lower limit of integration, we've evaluated the integral, and so now we actually evaluate the limit as a goes to negative infinity. Limit of a constant is the constant e to the 0 is 1. And now what do we have? We have e raised to the power 2, and we can think of it in our infinity arithmetic. This is negative infinity cubed, which is why I went through that review at the very start. Negative infinity cubed is still negative infinity. And 2 times negative infinity is still negative infinity. And if you have a negative exponent, we could write this as e raised to the negative infinity, but negative exponent, let's kind of thought process here. This is e to the negative infinity. Negative exponent means you go 1 over. But we know what that is. This is 1 over infinity, which is 0. 1/6 times 1 minus 0. 1 minus 0. And that is, I'm running out of space here, equal to 1/6. All right? So there's plenty to do, but I think if you keep your wits about you and keep the procedure in mind, replace with a limit statement, evaluate the antiderivative as usual. If you need to, use dummy limits, but go back to the original variable. Now, evaluate at the top minus evaluate at bottom. Simplify if you need to, and then evaluate this limit. So that's the procedure for this bit.